Hydrogenation of alkynes is the addition of hydrogen to a triple bond in the presence of a catalyst. It is important to note that when an alkyne is hydrogenated, we are simply adding hydrogen atoms across a triple bond, so either a double bond remains or only single bonds are present in the compound. If the final product contains a carbon-carbon double bond, it is called an alkene. If all single bonds are present, an alkane is produced. Alkenes can be hydrogenated, and the same thing is true for alkynes because they also have pi bonds. So if you look at an alkyne, you have one sigma bond and two pi bonds in the triple bond of the alkyne. You could either add one equivalent of hydrogen across the triple bond. If you do that, you'll end up with an alkene. But if you add two equivalents of hydrogen atoms across a triple bond, you'll end up with an alkane. And in that case, all will be left is one sigma bond. So if you take an alkyne and add two equivalents of hydrogen, you would get that alkane with two equivalents of hydrogen added. And this is done with a palladium catalyst or with platinum or nickel. A metal catalyst provides a surface for the hydrogen gas to fix to and add across the pi bonds.
The next method of alkyne synthesis is designated Lindlar's catalyst. Lindlar's catalyst is another method of hydrogenation of an alkyne. However, instead of reducing it to an alkane, it reduces to a cis-alkene with a Z stereochemistry. This is achieved by adding a poisoned catalyst among the hydrogen gas. The term poisoned is used because the catalyst added lacks the normal activity associated with the catalysts for reducing double bonds. The poisoned catalyst is made up of palladium, calcium carbonate, lead-2 acetate, and quinoline. When written into a reaction, Lindlar's catalyst is represented as palladium poisoned with traces of lead and quinoline. This reaction is represented as an alkyne reacting with H2 and the poisoned palladium, or merely H2 written alongside Lindlar. This reacts with the alkyne to produce an alkene, specifically in the Z-alkene. Take note that this reaction is the only possible way to reduce an alkyne to an alkene with the Z stereochemistry. As you can see with the second example here, Lindlar's catalyst is applied to the triple bond substituent of the cyclohexene to produce another alkene, again with the Z stereochemistry.
The final variation of alkyne synthesis has the outcome of the E-alkene. Similar to the Lindlar's catalyst, the hydrogenation of the alkyne stops at the alkene level, but in this situation the product has the E stereochemistry of a trans-alkene. This version is way less intense sounding than the Z-alkene Lindlar's catalyst, with how the alkyne was so-called poisoned in the reaction. The E-alkene catalysts are either of the two combinations, the first being a lithium ethanamine with ammonium chloride. The second would have the combination of sodium and ammonia. Both these combinations would have the same outcome though, of like an E-alkene. The main component to look out for when dealing with this scenario would be the metals lithium or sodium. These are generally significant catalysts to know when dealing with hydrogenation of alkynes. With the first example that we have for this alkyne hydrogenation into an E-alkene would be obviously the alkyne butene. With the reaction, the catalyst would be lithium, ethanamine, and ammonium chloride, and the product would be the E-alkene, which is a staggered formation butene, or butene. In the second example, which is very similar to the first one, we would have the alkyne as a pentyne. With the reaction, the catalysts would be sodium and ammonia, and the product would be the E-alkene that has a staggered formation of pent-2-ene. But remember that the hydrogenation of alkyne into an E stereochemistry alkyne can have different catalysts of lithium, ethanamine with ammonium chloride, or sodium and ammonia, but both instances have the same outcome, or a zigzag-looking trans-alkene.